working on power series, and there's a couple of things I want to do before we kind of continue from where we left off.
Professor?
Yes.
I'm supposed to remind you that we're supposed to do we're supposed to do the integral convergence today too.
Yes.
Problems.
Well, thank you for doing that. And Maggie, you missed out there. You were meant to remind Alexander, but he did it anyway.
Oh, she reminded me. She
did.
Yeah, she did.
Okay, so it worked perfectly. Yeah, what I will be doing is doing actually question 7. I've got it set up here, where we'll do the whole start to finish, right? And connected to that is what I'm going to do right now. I want you to imagine that we have a power series, and I'll make it whatever, that guy. It is possible, especially because the questions that you're going to do will look more like this. When you substitute in, have you noticed that quite a lot of the answers have x to the 3n, x to the 2n plus 4, right? Things like that. Now, we will do one of those question 7, but what I'm getting at is, suppose I did the ratio test the way I always would do it. There are a couple of situations that appear that I think are going to be helpful. If I just talk about them a little bit more. Can you imagine I got a situation that looked like this, right? We cancelled it, we did all the good stuff, and we got that, right? Just for argument's sake. Now, this piece here gets you 3, and so your answer ends up being that. Great. And then you would say, for it to converge, the limit, which is this, has to be less than 1, and we get that. And once you've written it like that, this number here tells you pretty much everything you need to know. Doesn't it tell you the radius of convergence is a third, and that the interval of convergence would be these two numbers, and then don't you just have to check the endpoints? So that would be a pretty standard one. Sometimes you get the ratio, and it might happen today when you do your homework, maybe later on even. And it ends up being a guy that looks like this. X squared, I'll make it x squared. Right, that can happen. Right. Now, what would happen next is, don't you find the limit of this, and you would end up with, essentially, can you trust me, that's 0, and you end up with that. Agreed? And what I used to do is, I'd say, well, that answer is 0, that is always less than 1, and that gets you a radius of convergence of infinity and an interval of convergence of negative infinity to plus infinity. And the reason for that is that since this limit is 0, it's always less than 1. Remember we doing that, right? I've got another way you can look at that that might help. If you think of it as being just that for the time of point, right? Then that is got to be less than 1. Great, right? The answer to the limit needs to be less than 1. So I'm just stopping here, right? I'm not doing this step. Now, if you divide both sides by 0, can you see where that infinity is coming from? I don't know if that helps or hinders, but isn't that another way of looking at the situation? And does it make a little bit more sense that if you divide 1 by 0, you get infinite? And so this is the relationship. See it working? Now, what happens when you get a limit as n tends to infinity, right? One of these guys. And let's say it ends up being something that looks like that. Well, that would get you infinity times x, it's called x squared, And then normally we would say, well, the answer is infinity, so it never converges. Let's stop there and say, okay, the limit has to be less than 1. So does it not make x squared has to be less than 1 over infinity? And isn't 1 over infinity 0? And do you know you get this? Well, I guess take square roots. We get that. Can you see then that in this last situation, the r is 0 and the interval of convergence is 0 to 0? So I just try to look at the two extremes. When the limit is 0, why do you get an infinity for an r and infinity for the intervals? And when the limit is infinity, why do you get 0 as your r value and 0 as your interval, right? So just another way to look at it. And I hope that helps at least one person who asked me something similar yesterday. Now, one last little situation, and then we'll be doing the question 7 that I talked about. Right, so we're doing this again. And let's suppose that after a bit of cancelling and all that good stuff, we end up with a thing that looks like this. N over 9n, n plus 1 over 9n, x to the 2n, right? Something that looks like that. Now, this becomes a ninth. So you get 1/9. Don't know why I keep putting that x right in. 1/9 x squared, right? Now, for this to converge, it has to be less than 1. What do you think I should do to get, eventually I need the absolute value of x less than a number. So what should I do next from this expression here? What should I do to both sides?
Multiply by 9.
Okay. Now, what you might be tempted to think is r is 9 and the interval of convergence is -99. But look again, it's not absolute value of x here. It's the absolute value of x squared. So what we have to do one more step. What will I do to both sides now to find out what the absolute value of x is less than? Because that's what we need for the r and the interval.
The square root.
And only positives. And does it seem reasonable that when you take the square root of both sides, you typically say there's a plus and minus answer? But in this context, isn't it always going to be positive because we're dealing with absolute values? So in this case, wouldn't the radius be 3 and the interval would be -3 to 3, and then we would test the two endpoints? Okay, now the reason why I put this situation in is because a lot of the ones that you're doing in this section, you very often get an x squared or an x cubed here, and you have to look at how to deal with it. Shush! The dogs are telling me a leaf fell somewhere. Okay, so the question I'm going to choose is question 7. The function we're going to get power series for is going to be x squared over 1 plus x to the 5. Actually, they call it x to the 5 plus 1, but I like the one first, so I'm writing it that way. So I'm going to rewrite this guy as x squared times 1 plus x to the 5. It's a pretty standard way of tackling this. And I am going to look at this fella, and I'm going to be really happy because doesn't really require much. Can't I just decide the substitution, right? Now, is the 1 over 1 plus x, does that have the -1 thing in it, or does that just have the plus thing in it? Over here, if you do 1 over 1 plus x and 1 over 1 minus x. If it's a 1 minus x, don't you just get x to the n? And then the other one, don't you get that? Remember those two guys? Okay, right. What am I going to replace this x here by to get a power series for this one? So think substitution. What will this x here get replaced by?
X to the 5.
So it's going to be -1 to the n, x to the 5 to the power of n. And then the next few lines are just to make things look pretty. Actually, I think I can do it in one line. If you take x to the 5 and raise it to the power of n, don't you get 5n? And if you bring this x squared in at the same time, won't it join the x to the 5n and get you x to the 5n plus 2 more? Are we comfortable with the power series of this fraction now? You comfortable where the bits came from? It's a bit ugly. 5 to the n plus 2 is not your typical guy. So I'm now going to get the radius and interval of convergence. We kind of avoided them, but this time I'm going to take it all the way through. So it's going to be the limit as n tends to infinity of an plus 1 over an, just like. In this case, it's going to be the limit as n tends to infinity of -1 to the n plus 1, x to the 5 lots of n plus 1 add 2, all divided by -1 to the n, x to the 5n. Oops, plus 2. Did you notice that the top one is not 5n, long pause, add 1, but 5 lots of n plus 1? Does that make sense that it should be that way and not just 5n and then add a 1 when you're finished? Now, this guy cancels. This guy cancels really well, actually. Can't we just forget about the negative ones because absolute values kill all of them? Right. A little bit messy here. So just to make your life easier, I'm going to do a little bit of work, and it's going to be x to the 5n plus 5 plus 2. So that's 5n plus 7. And on the bottom, it's going to be x to the 5n plus 2. Are we comfortable with that? Okay. You know that those x's are going to cancel. Would you agree? What do you get left over? And is it in the top or is it in the bottom?
You get x to the 7 on the top and x to the 2 on the bottom.
And that can simplify down to what?
X to the 5?
Yeah. Would you agree that this is a kind of weird exception? There isn't any n's worth worrying about, right? There's not an n over n plus 1. So can I just drop that now? Right, it's done its job. So absolute value, absolute value. So here we are. The limit of this ratio ends up just being x to the power of 5. Right. Now that should be less than 1, agreed? But we want to know what the absolute value of x is less than. This one's kind of trivial, isn't it? Because don't you just take the 5th root of both sides? But isn't the 5th root of 1 still 1? So we now have a radius of convergence of 1 and an interval of convergence of -1 to 1. Oh God, she's done it again. I am too easily distracted. Do you know her poo mat? She's ripped the bloody thing up and it's behind me. So she's either going to have to find a piece big enough to poo on or I'm in trouble. But I'm not going to fix it because I don't have time. So let's do the test. X is -1 is going to be one of my tests. X equals 1 is the other. And the power series that I'm doing to is this guy here. So it's going to be sigma n equals 0 to infinity, -1 to the n times -1 to the 5n plus 2. Now you can combine all of these and you get -1 to the power of 6n plus 2. It's kind of a weird question, but that's what you get. What does well, actually, I don't even need to calculate. Is that thing going to converge or diverge? I can tell right now. Adding up -1 to the power of 6n plus 1. Is that going to converge or diverge?
Diverge.
Yeah. Would you agree it's just a whole load of ones added up? It's going to diverge. So I'm just doing that technically through the divergence theorem. If I do x equals 1, it doesn't really do much. So what you get is -1 to the n times. Isn't that basically just 1? And would you agree that that also diverges? And so we are finished. The radius of convergence for this power series, which is him, is 1. And you can only use it, or it only converges at least, between -1 and 1. So as long as you choose x's in that range, this guy will look like that.
Can I see the other page real quick?
Sure.
Okay, I'm good.
Okay. Now, still on power series, but we're now going to look at how to integrate and differentiate power series. Right, if a power series is an infinite polynomial, shouldn't you be able to differentiate it? Shouldn't you also be able to integrate it? We're going to do it with the sigma notation version of it. And how does that work? Right. Well, here it goes. Suppose f of x is sigma n equals 0 to infinity, some guy an x to n. Would you agree that's just a kind of bog standard power series, right? If you differentiate okay, think of an as being a constant, right? Just a term. If you differentiate an, right, 5, x to the power of n, isn't it the power rule? Multiply by the power and reduce the power by 1. Great. So you multiply by the power and then you reduce the power by 1. So far, so good? Now, a little hiccup. Do you know when n equals 0, you have a 0 here, right? X to the 0. That's what gives you the, the constant term, right? The 1 plus x squared thing, right? When you differentiate that, doesn't it disappear? Right? A number when you differentiate it. Because of that, you add 1 to the integral. So do you see that the sigma, do you see that that 1 is to take care of the first term? And then you could do that if you wanted. Basically, just wind it back one. This is correct, and this is correct. Or you might say, well, what did I do to get from here to here? Well, if you think about adding 1 to these guys or taking 1 away from these guys, but in this case, adding 1, if n becomes n plus 1, right, going like this, wouldn't 0 become 1? So I'm basically just taking the series and shifting it. I'm not changing its value, just the way it's written. This version here is considered a little bit prettier. Why? Because it has an x to the n in it. But this answer is totally correct. Well, let's show you how that works. Suppose I have a power series n equals 0 to infinity of 7 to the n x to the n over n factorial, right? Then if you want to differentiate it, you just make this 1 to infinity and you power rule it. So n times 7 to the n x to the n minus 1 over n factorial. Are you comfortable with that? Just differentiate the term and remember to move your sigma up 1. That's to take care of the number, right? So you don't have an, if you didn't do that, wouldn't 5x to the nothing kind of cause problems? If that's how you differentiate, then how do you integrate? Well, if you want to integrate this function, first thing is, do you notice that n0 is still there now? Don't numbers, when you integrate them, they don't disappear, don't they just have an x tagged onto them? Okay, now what do you do with that? You do a power roll on it, and that is add 1 to the power and divide by the new power plus c. So if you integrate a power series, you get this. Power series are a little bit prettier, aren't they? Because you don't need to worry about moving the sigma value. It's always there. But you then have to remember to do a plus c. But don't you do a plus c when you integrate everything? Right, so let's put that one into account then. Right. Here's the same guy. If I wanted to get the power series of the integral of f of x, I would take that guy there. And I'd add 1 to the power and divide by the new power. So I would have 7 to the n, x to the, I don't know why I'm putting brackets around it, and I would then divide by the new power. And although it doesn't happen very often, when it does happen, you have to be aware of it. Oh, let's see. Style points. Don't often get much in the way of style points in these questions, but they do happen. What is n plus 1, just n plus 1, times n factorial?
Wouldn't it just be like in parentheses n plus 1 all factorial?
It would be. And that's style points, right? Making things look pretty. You're not going to see that happen as much, right? Can you imagine most questions, that's probably, the thing you got is what you get, right? But you might get some interesting things. You might get a cancel somewhere. I could imagine a situation where there was an n plus 1 up here. Wouldn't it cancel that out and, off you go and do other things. So have it in the back of your mind, maybe I could do something a little bit better, right?
And I have a quick question.
Yes.
So when we're doing this, we basically like almost kind of ignore the factorial because it's going to do the same thing no matter what. We just really care
It's
about
just a number.
integrating the
Yeah.
x. Like in factorial is just a number. So that's why we don't like worry about it too much.
No. In fact, aren't
Okay.
you really just doing power rules with x's, or differentiation power rule with x's, or integration power rules with x's, right? Okay. I think I should focus on doing this before we go into the whole question where you create this and then you differentiate it, which are quite long. So let's suppose I have a function and it's that guy. So I'm making this a harder version, right? Just playing about with it, making it harder, right? If you want to differentiate this one, start at 1 to infinity instead of 0 to infinity. And then isn't the only guy that you need to worry about is him. Won't all the other things that my finger is covering stay put? They won't change in any way right now. So I've got that guy, I've got that guy. I'm going to multiply by the power. Okay, what will the new power of x be? I've multiplied by the power and now reducing it by 1. What will the new power of x become?
Just 2n.
Now that could well be the answer. A lot of the time it will be, but not this time. There is some style points. Can anybody see any simplification, cancel, reducing, whatever you want to call it? Because I can.
The 2n plus 1s.
Now this is 2n plus 1, agreed. This is 2n plus 1 factorial, so they do interact. But it's not like this cancels that totally, right? It does simplify, it cancels, but not completely. It's not like they both disappear and that's all that's left, right? So I'm writing down all the pieces that don't matter because nothing's happening to them. What happens when a single 2n plus 1 cancels with a 2n plus 1 factorial? What gets...
Two factorial?
Say it again, Eric, I interrupted you, sorry.
Would it turn into 2n factorial?
Yeah, make sure you put little brackets around it. There. Are we feeling comfortable about how to differentiate and integrate? Do you want another integration, or can we move on to actually tackling because they're big, these questions take forever, right? You want one more, or are we good? I can't see. We're good, thank you. So I think I'll pick the first one because it's probably a good idea to not go too far out the way. So in question 8, the function that we are going to create a power series for is that one. And that'll be like part A of the question. And then part B is that we are going to find the integral. So in this case, I'll split it as x to the 6 times 1 over 1 plus x to the 7. Do I have my guy? I don't have it. Okay, don't matter. Hopefully you already know what that's going to turn into. Is that the one with the minus 1 to the n in it, or is that the one without it? What is 1 over 1 plus x to the 7? Does it have the minus 1 to the n in it or not?
It does.
Agreed. So, and typically it would be x to the n, right? But in this case, it gets changed, doesn't it? And it gets changed by replacing that by 7. Are we comfortable with that? We've done a few of those by now. Now, if you put all the pieces together in one go, you've got that guy, you've got x to the 7n, and you add in this guy, you've got 6. Are we we're confident with that? We're used to that process. Right. Now what we're going to do is we're going to integrate this guy. Technically, we're integrating that guy. Actually, if you gave me the job of integrating that guy, wouldn't I do a U sub because it'd be a lot less work? But let's just pretend that there wasn't an easy way to. Can you imagine really weird fractions that you couldn't integrate directly? You know, x to the 4 over 1 plus x to the 7, right? That would be a killer, right? Right off the bat, right? So, you know, this technique could be useful. So that means that we are basically going to be integrating this power series. And since this is notes, I'm putting in every line I can think of. Now, when you integrate, don't you keep the n equals 0 part. Agreed? So far, so good? Right, now, you integrate this. That means you add 1 to the power. And then you divide by the new power. And you add a c. Are you comfortable with that? Add 1 to the power, divide by the new power. And because it's an integration, don't these guys stay put, but you do remember to add a plus c. Now, some questions, that's the answer, right? You might actually find out what c is. Does anybody know how you find out what number c is? If you know what the integral function is equal to and you evaluate it at 0. So that guy is essentially, you remember, big capital of 0. Just if you're curious, that's what it's equal to. But this question did this. Now we know what the integral is equal to. It's a power series. So this is a bit weird. But nonetheless, it's doable. And we're going to evaluate that at x equals 0 and x equals 0.2. Well, when you plug 0.2 in here, you get a power series where the x is replaced by a decimal. So it's -1 to the n, 0.2 to the power is 7n add 7. All divided by 7n add 7. Take away this power series with x equals 0 in it. So it's going to be n equals 0 to infinity, -1 to the n, x to the 7n plus 7, and that x should be a 0, to 7n plus 7. Okay, I know that's weird. What do you think that power series adds up to? Aren't you essentially adding an infinite number of zeros together? Agreed? 0 to the 7, 0 to the 14. So that's take away 0. And so you are left with this fella. Now, thank goodness they went and said something that's going to help us, because they asked us to approximate this thing. Do you recognize that this is an alternating series and that it converges? We have to assume it converges, which it does. Now, if you are an alternating series and you converge, right, isn't there a way of knowing how many terms you need to get any given accuracy? So in this question, you're being asked to approximate it to 6 decimal places. So I'm going to take that job and do it over here. So I have an alternating series. I know it converges. And if you want it to correct to 6 decimal places, don't you need to solve an plus 1 is equal to 0.1, 2, 3, 4, 5, 6, and you put a 5. You remember doing that with alternating series. In this case, I don't care about that. What I do have is 0.2 to the power of 7n add 7 all over 7n add 7 equals this ridiculously ugly decimal. You still with me? And I just made a mistake. Someone tell me what my mistake is.
The n plus 1 needs
I
to be
forgot
plugged
n.
in.
Right. So that gets you 7n plus 7, and 7 is 14. And if you put an n plus 1 here, you get 7n plus 14. Okay, so it wasn't that different looking, but it is important. That is impossible to solve algebraically. Correct, Kira? Kira, you said you did it on Desmos. Is that correct? You did things like this on Desmos. How easy was it to do on Desmos?
So easy. You go y equals and you replace n with an x, and then you say the second line is y equals the 0.0000, and then the intersection point. You can literally just click on it.
Perfect. So I'm going to do that because I've never used Desmos to do that. Normally I do a very boring technique. You try n equals 3, and then you try n equals 4, then you try n equals 5, and one of them works. Because it's never 23, right? It's always, 5, 6, 7, right? But that's not very successful. So if you can bear with me for a few moments, Kira is going to take over the job of instructing me. And I will try and follow her instructions as best I can. And hopefully you lot, if you want to do it this week and watch this bit of the video, even if it's only the bit at the end, that's fine, so that you can use Desmos to do it yourself. I'm almost there. There's Desmos. Move over here and okay, I think I'm ready. So I have the equation here. If you can't remember it, if you can, that would be great. So let's try it out. Okay, so I got Desmos. So I type in y equals, in this case, 0.2.
I'm not sure if it's sharing your screen.
Oh, can you see Desmos now?
Yeah, there we go.
Okay, so click on it again then. So y equals 0.2.
Mhm.
0.2 to the power of 7n, so that becomes 7x plus 14.
Oh, careful!
That didn't work. No.
Yeah, it always takes it out of the. It always takes it out of there. It drives me crazy.
Right. Okay.
You need to use a parenthesis.
You need to do what?
Use parentheses, I'm pretty sure.
You know,
That way
inside
it'll
the
know.
power. Oh, yeah. Just
That way
to
it
force
knows
it.
you don't want to, yeah.
Okay. Well, as I say, I've not done it this way before, so there we go. And then I can click out of that. I should be able to do a divide. Perfect. And just a 7x add 14, which is quite a weird looking function. Okay, what do I do now again?
So the second line is just y equals 0.000005.
Okay. Boom. Now I can't see, I know what it is. It's this blue line. So how do I get to the intersection point? Do I just click on that? That doesn't make
Yeah,
sense.
the two little gray dots.
Can't see it.
So it should be there's a little gray dot. If you zoom out just a little bit, it should be making one on the. It's almost at -1.
To find
Right.
them, you
You
might
have to re-click on the blue line.
Re-click on the blue line. Click. Ah.
Yeah, and then zoom in, and then you just have to. And then the little gray dot. There's one at 0, and then there's one at -1, almost -1.
Oh, it may just be the reason I'm hesitating here is I don't want negative numbers. Don't you want 1.7 and 3.2? And so I'm trying to interpret that, and the only interpretation I can get here is that it only needs one number. That doesn't make me feel good. Let's double check. That is 0.2. Check, it is that. Check. Is it that? Yeah. That's a power. Yeah. And when does that equal this guy? Let me check something. If you do 0.2 to the power of 7, which is essentially the first number, and you get that guy, and then you divide it by 14, you get that guy. Ah, it works. I'm sure when the number is 3.2 and 4.2, this will work really well, you know. This has to be interpreted a little bit differently. You know, you need at least one term, agreed, to make this work. And so the nearest number I can use was 0. Now, 0 doesn't mean one term, doesn't it? Just mean A0. It means the first term, because I'm counting from n equals 0 to infinity. So that actually did work. So let me show you. I believe it worked anyway. That you should be able to do it with one term. So if you do this power series, actually, if you do this power series only at 0, you will get 0.2 to the power of 7 over 7. And that guy, 0.7 to the power of 7 divided by 7. Okay. Plus the next term then.
You put in
No.
0.7 instead of 0.2.
No, 0.2 to the power of 7, check. And yeah, I'm just plugging in n equals 0 and getting that. That guy there is 0.0117649.
On your calculator, you put 0.7 to the 7.
Oh, darn it in space. 0.2 to the power of 7. Oh, okay, and divide that by 7. So the correct answer is 0.1234, 5 more 2. Perfect. Oh God, this power series converges so quickly. You only need one number, the first value, and the first value happens to be a tiny number. Okay. That one looked weird, but can you trust me that if it's a number like 3 or 4, it will make much more sense. So I'm actually going to stick to that. I like that. So what our conclusion would be that in this question, if you wanted to have it correct to 6 decimal places, you would only need to use n equals 0, which is actually the first term, because my series starts at nothing. Interesting. I get time? Yeah, I think I do. Right. There we go. While I'm getting myself set up, you want to say your last name for attendance? So, question 9. You have a power series already given to you. And you're being asked to find f dash of x. Now, if you take this guy, start at 1, multiply by the power, reduce the power by 1. You got that guy? if you shift them back to zeros, you basically add 1 to everybody. Can you simplify this power series? N plus 1 on the top. Actually, we did something very similar to this, didn't we? N plus 1 on the top and N plus 1 factorial on the bottom. What does that simplify down to?
N factorial.
Okay. Oh, wait a minute. So I did that little trick that this is correct, but if you want to kind of make this x to the n, basically just add 1 to everybody and, you know, take 1 away from that. That's a kind of compensation thing, and that does it. If you write down this power series in full and you write this one down in full, they are the same one. So you're just going to trust me in that. But the important thing, or the interesting thing, is that aren't they two the same? What function do you know who's the same as his derivative?
It has to be E.
So guess what? We have just found the power series for the exponential function. So up to this point, haven't we only found power series for fractions? Is that not mind-blowing that e to the x is actually a power series? To me, that is fascinating. I want to, for the last 2 minutes or so, I want to show you something really cool. I think this is really cool. It still amazes me, and it'll probably always amaze me, that a power series and e to the x are the same thing. So here is y equals e to the power of x, right? Does what exactly e to the power of x should do, agreed? Now, if you take the power series that I've written down here, and you're just going to trust me, there's y equals. So if you put in the first one, you get 1 times x to nothing, and then you get x squared over 2 factorial. So that's x squared, right, divided by 2 factorial, which is 2. And then you've got x cubed. Oh, I forgot my x. So before that, you have an x divided by 1 factorial, which is just 1. Then you have an x squared divided by 2 factorial, which is 2. And then you have an x cubed divided by 3 factorial, which is 6. And then you have an x to the 4 divided by 4 factorial, which is 24. And then you have an, what's the next one? X to the 5. This is the last one. Divided by 5 factorial, which is 120. Now, I haven't done an infinite polynomial, but if I zoom out a little bit, would you agree that the purple guy is very like the exponential function, especially for, you know, decent sized values of x, right? It's not so good over here, but if I zoom in a little bit, there. Can you tell the difference between e to the x and that polynomial that I've just written? So between -1 and 3, well, 2, or whatever, if I stretch, if I move it up a little bit, you get a little bit more of it. Can you see it's a really, really good fit? Now, can you imagine I kept on going? Wouldn't it be even better fit and a better fit and a better fit for eternity if I could do it forever? So isn't e to the x just an infinite polynomial? That is mind-blowing. E to the x is an infinite polynomial. And if you wanted to know what e was equal to, couldn't you take that power series and replace the x with 1? And just try and evaluate it. Well, that is a, oh God, I have terrible memory. I will not be able to teach you tomorrow in person because I have a meeting that I have to be at, and when we have meetings, we can't, somebody's going to have to miss a class, right? Because there's not one time where we're all free. So I get nominated to miss my class. What will happen instead is I will be putting up a video on what the lesson would look like in Canvas. So you can watch what would be the rest of the section that we haven't covered. And I'm going to have to change the homework assignment to reflect that. So your test 4, online test 4, will finish on this section, right? So what's left? Basically finding derivatives and integrals of polynomials, right? That's as far as we're going to go. So I won't see you tomorrow. So you don't need to turn up. You can, maybe you can have a little extra lie in, but watch the video. It won't be online until quite late in the evening because I have to make it and do a whole lot of the other stuff. Okay. So bye-bye from now. I will hang about if there's any questions.
Yeah, well,
Thank
you're
you. Have a
making
great
it.
weekend.
Whoa, I'm
Good.
getting 3. Go for it, David. You were first, I think.
Will this also affect the stat class?
No, I'm only, it's only that 1 hour that I'll be doing the meeting. The rest of my classes will be taking place as usual, David. Okay, who's got the questions? And I'm
I
very
have one.
disappointed in you, Maggie, being okay about the whiskey thing. You're too young to go do whiskey. Ever. Start drinking it when you're 40. Right, Eli? Nod your head. Don't start drinking that stuff till you're 40.
That's
At
right.
all. Okay. Right, who's got the first question?
I have one real quick.
Yes, darling.
So on the question, second to last question we did, the one that had 0.2 and 7n plus 14.
Yes.
You added 1 to the power of -1 to the n, right? And that got rid of that. But how did you get 7n plus 14?
Oh, on the bottom, it said 7n plus 1. Right, that was the original. When you
Yeah.
plug n plus 1 in it, you get
Wait,
7
also I
lots
can't
of
see.
n. Oh, I think I may have made a mistake. I think it was not 7n. Was it 7n plus 1 or 7n plus 7? Because I think
I have 7n plus 7.
Okay, so that's good. So if, oh, you still can't see it. Darn it, heck. Here we go. So the other stuff, but on the bottom you had that, right?
Yes.
Right. So when you replace the n by n plus 1, you have that. You then have 7n plus 7 add 7. And that's why that became 14.
Okay.
So provided the bottom was that. Now, if the bottom said 7n plus 1, then you would eventually get 7n plus 8 on the bottom, right?
Okay, and the same thing happened in the power, right?
Yes.
Okay. That
For the
makes
same
sense.
for the same kind of reason.
Gotcha. All right, thank you very much.
You are
Have a good day.
welcome. You too. Right, who's for the next question?
You said that the test tomorrow is going to be a little later in the evening.
Not the test, the lesson will be a little bit later in the evening. The test will be available at 1, but I wouldn't do the test until after you've seen the last video, because there'll be stuff in that that will be, will be useful.
Okay. Thank you.
Right. Anybody got a question? If not, it's bye-bye. Maggie?